In this presentation, we have to talk about the theory of alpha decay. Consider a proton approaching an atomic nucleus. As the distance from the nucleus decreases, the electrostatic force of repulsion is started to act on the proton. As the proton moves against this opposing force, the potential energy of the proton gets increased. We know that the nucleus is having a positive charge, then proton is also having a positive charge. If a proton is approaching towards the nucleus, an electrostatic repulsion is developed in between them. To overcome this electrostatic repulsion, work has to be done. That work done is called as potential. You know the definition of potential. Work done in moving a unit positive charge from infinite distance to a particular point against the opposing force is called potential at that point. So with respect to the distance of separation, the value of potential is justified. If the distance of separation is less, the potential would be more. However, when the proton comes closer to the nucleus, say 4 Fermi, the nuclear attractive force begins to act on them. When a proton is moving towards positively charged nucleus, a repulsion is developed, even though when the proton comes closer to the nucleus, say 4 Fermi, if the distance of separation is 4 into 10 power minus 15 meter, instead of repulsion, an attractive force is developed because of attractive nuclear force. At about 2 Fermi, if the proton is reaching a distance of 2 Fermi from the nucleus, the intensity of attractive nuclear force is increased. If you plot the potential along the y-axis and the distance of proton from the nucleus along the x-axis, we get a curve of this type. See, x-axis is the distance of separation of the proton from the nucleus. Y-axis indicates the potential energy value. See, this curve represents Coulombic repulsive potential, but this region represents attractive squirrel potential. Here, an electrostatic repulsion is possible between the proton and the nucleus, but within this squirrel potential, the nuclear forces are dominating, therefore an attraction is acting on the proton. So the potential value is negative, but here the potential value is positive. Now we have to apply this theory for the alpha particle. If we consider the alpha particle emitted by a radioactive nucleus, then those alpha particles can be supposed to exist inside the nucleus at least for a short time before emission. The alpha particles can only be held inside the nucleus by short range but strong nuclear forces. Before the emission, the alpha particle is existing inside this squirrel potential because of the nuclear forces. If the size of the nucleus is large, say uranium is taken for our consideration, because of its larger size, the distance of separation between the nucleons is more. If the distance of separation is more, the short range strong nuclear force is reducing its value. Therefore, the Coulombic force is started to dominate. See here, XZA represents an element. If it emits an alpha particle, the mass number is reduced by 4 unit, whereas the atomic number is decreased by 2 unit. Here, one alpha particle. Then the repulsive force between the alpha particle and the heavy nucleus, that means the repulsive force existing between this element and this one, is F is equal to 1 by 4 by epsilon naught Z minus 2 into E 2E divided by R square. You know the Coulombic repulsive force, F is proportional to Q1 Q2, F is inversely proportional to square of the distance of separation. Here Q1, this is Q1, charge of the daughter nucleus, this is charge of the alpha particle. Distance of separation is R. So to remove the proportionality sign, we are using this constant 1 by 4 pi epsilon naught. We know that F is equal to minus grade V. Gradient of negative potential is called force. So F is equal to minus dV by dr. So minus dV by dr is this much. Then this is modified as z minus 2 into 2e square. So this is changed in this form. So dV equal to minus of 1 by 4 pi epsilon naught z minus 2 e into 2e divided by r square into dr. Then dV equal to minus 1 by 4 pi epsilon naught 2 into e square z minus 2 dr divided by r square. Then if you integrate this, we can get the value of v equal to 1 by 4 pi epsilon naught into 2 into z minus 2 e square by r with a positive sign. Here r is the distance between the alpha particle and the nucleus. Suppose small r is equal to capital R. Here r is our nuclear radius. Then this equation is modified as v equal to v maximum. Potential is reaching its maximum value. V maximum is equal to 1 by 4 pi epsilon naught 2 into z minus 2 e square divided by capital R. See this diagram. Suppose the distance of separation is equal to r at this point. If the particle is reaching this region, that is nuclear radius region, then the potential is having its maximum value. This is maximum value. So at the small r, distance of separation is equal to radius of the nucleus, then the potential is reaching its maximum value, V maximum. Then V maximum is equal to this much, but nuclear radius r is equal to r0 a power 1 by 3. Then put up this value. At r lesser than r, if the distance is reduced further, which means that the particle is present inside the nucleus, the potential is having maximum value at r equal to r0 a power 1 by 3. This is known fact. At r lesser than capital R, within the nucleus, the strong nuclear forces come into play and the alpha particle gets confined to the nucleus. Suppose the alpha particle is within the nuclear forces are dominating. As a result of this, the alpha particles can have negative potential energy within the nucleus. Say here the potential is negative spiral potential. This is attractive potential, but this region is a repulsive potential region. The region of negative potential is called potential well, whereas the part of positive potential is called the potential barrier. For uranium, the maximum value of potential is 26 MeV. If you substitute all these values, in the case of uranium, we have had the potential is 26 MeV. That means the depth of the potential is 26 MeV. This value is 26 million electron volt. But if you think about an alpha particle coming out of the uranium, the energy of the alpha particle is near about 4.2 MeV. So the classical mechanics does not accept this statement, because how does an alpha particle of energy 4.2 MeV come out of the depth of 26 MeV? However, the quantum aspect provides excellent explanation for this puzzle on the basis of quantum tunneling. Here, the key factor is, if the size of the nucleus is large, the separation distance between the nucleons are more. Therefore, the nuclear forces are not dominating the Coulombic force. The nuclear forces are less. At that moment, the repulsive forces are dominating, so that an alpha particle is coming out of the nucleus. So the alpha particle are coming out of the nucleus. The system is maintaining its stability.